Okay. Yeah. Okay, I think we should start. We should. Our first day is a little bit chaotic. Yeah. Well, welcome. Good morning. Yeah. Welcome everybody, especially the guests from the international guests from the other universities. So for this conference, the first part is about the short course, that's sponsored by the U.S. National Scientific Foundation. So this is a 2 days workshop. Well, I maybe talk. I try to talk slowly, and I assume. So we just this is new stuff. I assume some people maybe very well already understand already, but some may be new. So I just try to speak slowly, and I hope we can discuss, and not just the short, not just I'm teaching, you're learning. It is discussions. So if you have any questions, so I can stop and we discuss. So we want to make sure you can get some benefit, not just take a long time fly here, okay, and didn't get anything beneficial. So that's what I don't want to. So therefore, I just hope you can stop me at any time if you have questions. So we like to discuss, So actually, this short course we have 2 days. Yeah, today just I give the talk. Tomorrow will be other lectures. So this could be, let's say, could be new to some students. Could be, in challenging. So some, people or some students may not agree with them. So as I said, this is pretty much like, workshop, something like that, or working shop. So we just work together, try to get some kind of consensus on the vortex, because vortex is really a challenge. We know the vortex every day, everywhere, but we don't have exactly, definition or, correct understanding for vortex. This is really a very challenging topic, but this is important in science. We just cannot. We don't need that. We don't need a vortex. We don't need quantified vortex. We don't need studied vortex mechanism. We cannot say that because it is important. It is the driving force, especially in the turbulent flow, I think. But unfortunately, most of the real flow is turbulent flow. So therefore, this is an important topic. I think that's why the U.S. NSF supported this, short course and conference. They also want we can get some kind of understanding or some agreement, consensus, or something like that. So I'm very appreciate your coming. Yeah, no matter you're supported by NSF or not supported by NSF, some professors they are supported by their institution. So I really appreciate it for that. Frankly say, this is your new stuff, a new topic. It's not very popular in the United States yet, not yet. Yeah, it's not very popular in Europe. I think not. I believe, of course, not in the third world. They may don't know this concept yet. They only read the textbook. But this concept is directly against the textbook, the fluid dynamic textbook. So that could be a challenge. Okay, let me start. Okay, but as I say, well, we have 1 day. We have a lot of time for discussion. Don't worry to interrupt me. So I welcome the discussion, welcome challenging, welcome different opinion, welcome to against me. That's what I said. As I said, well, we pretty much talk about a mathematical issue. As I said, any theory, if we find one counterexample, this theory is collapse. Same thing for the Lutex. If we find one counterexample, the Lutex theory, we should put in the trash can. One. You don't need two. You don't need two. The two is not necessary. One counterexamples. Well, but for any theory, you get one, they failed. Be careful with that. I hope you can give me any counterexamples to my theory. So if you find one, we say, well, sorry, your theory should, put the rest place or trash can. That's well, we will see how many contradictions the textbook, how many contradictions the traditional theory. You can find how many. I said, one is enough. We really don't need two. We can find how many contradictions from the textbook, how many contradictions from traditional theory, classical theory, we will find it. That's the reason why we still don't understand turbulence. Okay, let me start the talk. Well, this is part one. I have 4 lectures, maybe slowly, repeatedly, but as I said, this is not a research report. That's as I said, this is the teaching, education, discussion. What's wrong with that? It doesn't work. Well, I have to use. Well, I don't know why. It doesn't work. I have to use this. It doesn't work either. What's wrong there? I think I should start.
Click on the.
Click what?
Click on this. Okay. They're trying now?
Yeah. Okay. That's the outline I'll talk. But today, I just talked the traditional methods for vortex. Well, of course, history cannot start from today. We have long history about the vortex. So that's the first talk. We talk about vortex definition and examples. Then we talk first generation. That's vorticity based. Then we talk second generation. That's vorticity, vortex identification criteria. That's popular now. That's popular now. People use it in engineering. And a little bit of mention about the third one. Well, I think there shouldn't be many, challenges for the physical definition for vortex. That's from Google. The vortex is a mass of fluid, such as liquid, gas, or even plasma, that spins around the central axis. So there are 2 important things. One, you should have axis. Second, fluid should rotate around this axis. I think this is very basic physical meaning for vortex. I'm not sure we still have challenging with that. Yeah, that's we from the Google. But unfortunately, in our textbook, in our traditional theory, classical theory, there's a vortex is vorticity. Well, how to link the vortex is vorticity? How to link them? There's no way to link them. One is a physical, where people can see it. The other one is the mathematical. And that's the vorticity, we say Q of the vorticity. There's two different things. How to link them? They're same, or they're different, or they are totally no relation. So that's the question. So vortex is ubiquitous in the future, in the nature. Well, this means vortex should be a vector. Should be a vector, because you talk about you have axis, you have rotation. Axis rotation, this is vortex, the basic definition. But unfortunately, all of this vortex identification method now is a scalar. So that cannot be a definition for vortex. Vortex, you need to have axis. You need to have rotation strength. You need to meet these two conditions. The physical there, you cannot change physics. People cannot change physics. You can change mathematics. Because mathematics is people understanding the physics. Physics cannot change. Axis, rotation. If we don't have the two, you cannot call vortex. Okay? So all of this vortex identification is a scalars. Most popular vortex identification methods. So there are only two candidates left. What are two candidates? One is vorticity. The other one is nutex. So far, according to our knowledge, we only have two factor definition. Because this conference talks about definition for vortex. Only two candidates. Because the others, you don't have, axis. The vortex is really how to rotate it. You don't have axis. Axis is a vector. So you understand what I'm saying? We talk about the definition of vortex. You must have two. One is the rotation axis. The other is rotation strength. If we don't have two, please take a rest. We don't talk about that. Well, if you don't agree, welcome any time. Okay? So we don't have two candidates so far left because others, no matter what kind of identification method, you're a scalar. Vortex is a vector. How you use a scalar to define vector? How to do that? So then we check, is the vorticity definition for vortex or the nutex is the definition for vortex? We will see, we check. Well, we say vortex is everywhere. Most, we can find it is like a tornado, like a hurricane. They call it tropic cyclone. And half flow, there's some student studied half flow. And even space science, like galaxies, they all like vortex. Well, when they meet the conditions, you will see that they have axis, they have rotation. That's the two factors. Well, we have many. We have wingtip vortex, we can see when you take aircraft. So even at home, the toilet is a vortex. So we can see the vortex. Well, also, I will repeat it, or I will, explain this. We talk this vortex is the global moving, global motion. But then we talk about vorticity. Then we talk about a vortex is point. There's a difference. They are different. One we talk about point, the other one we talk about global. Something like a hurricane, like a tornado. This is a group of fluids. So we must make a difference for them. But on the other hand, all of mathematical definition is for point. None of definition is for group. Mathematical definition, none of them. So for example, what's mathematical definition for this room, for this classroom? What's mathematical definition? What is mathematical definition for car? What? Alpha, beta, or gamma? All of definition in fluid dynamics is for one point. Mathematical definition. You say, the turbulence, well, what is mathematical for turbulence? Turbulence is a group. We only can talk about one point. At one point of turbulence flow, one point is a vortex. We only can give the definition for one point, not for, the CO building. What definition for CO building? A plus B squared plus C? Or what's the definition? We don't have definition. We only have definition for one point in the fluid dynamics, like temperature, like pressure, like velocity, like vorticity, all for one point. So this is talk about vortex. It's a global motion. Okay. Of course, when we define the point, we want to use this definition for the global movement. Of course, otherwise useless. Well, this is Dr. Schultz here. This is he made a video. I cannot play all of them, but I don't think. Unfortunately, I don't know how to. I can play. That's Dr. Schultz here. He made this. Yeah, he just show how the 2D, unfortunately, 2D like one common vortex street showed how the vortex formed. Yeah, he used 2D DNS really. Yeah, but then it released the particle. They used the mutex. At that time they called mutex. Mutex. And mutex, when mutex is blue or red, that means the mutex center. This is matched particle moving. I think you also have vorticity, right? Unfortunately, he made some mistake. He talked about vortex. He talked about rutex. Rutex is a mutex. Vortex is vorticity. At that time, vortex is vorticity. Right? Yeah, vortex is vorticity. You will find the particle match the mutex is rutex. Don't match the vortex. Vortex is vorticity at that time. But this is made in like 2018, so long time ago. At that time, everybody think vortex is vorticity. Sure, period. But unfortunately, the simulation doesn't support this. Yeah. So vortex have no relation with vorticity. Yeah, no correlation with vorticity. You will find it. They match the black one. He made a lot of this. I only show one of this. But this more clearly show how this particle moved. So they followed vorticity or followed, nutex. But as I said, at that time they called it rotex. Rho is nutex. At that time, vortex is vorticity. Because people call vorticity vortex. Same thing. Vortex is vorticity. So this is still some misunderstanding at that time. Yeah. But you can check that. Yeah, you can check. Well, you can do it by yourself. 2D, everybody can do it. I think the computer capability, everybody can do it. You will find it. It's the vortex match the nutex or match the vorticity. Unfortunately, vortex vorticity, they don't have any correlation in boundary layer. In viscous flow, there's no correlation. But the 2018 people call, even Dr. Xu called the vortex vorticity. Vorticity is vortex. Then we discuss, then we say, gosh, the vortex is not vorticity. Vortex is nutex, they call it rotex. Well, this is very, very, very hard for people to change mind. Because people say vortex is vorticity for hundreds, 160 more, maybe 170 years, they say vortex is vorticity. Because, well, we understand that this guy is very great, but they don't have computer. They cannot do simulation. They even cannot do, experiment. Unfortunately, this textbook, this very famous guy, this very famous theory, sorry, you are all misunderstandings. You are all misunderstandings. But it is hard to change people's mind. It is very hard, yeah. So you guys here, yeah, I'm glad you probably become first, group of people. It's not vorticity. So, well, it makes people surprised, make students surprised. But your book said what is vorticity. Clearly, why is it not? Now it's not. Well, what do? We have to respect the science. We cannot close the eye. I don't want to see the science. I don't want to see the experiment. I don't want to see the simulation. I only trust the book. I don't think this is the attitude to scientific research. I don't think that. We must respect the numeric simulation, experiment, and science. That's why we are here. Yeah, even some very young students, you may be the first group where say, the vortex is not what is it. It doesn't make nonsense. Why is the vortex? You can check that. I think Dr. Xu here, he made a lot of movies. They can prove that. Yeah. That's even for 2D. Well, I think we also made quite a lot of videos. Well, this is for the boundary layer flow transition. Boundary layer flow transition, yeah, by DNS, yeah, by direct numeric simulation. Well, we did this a long time ago. Frankly, tell you, long time ago. I think this is made in 2018 or something like that, or earlier. Well, we really made this in 1995. 1995, long time ago. long time ago. This made in 2018 by Nutex. Well, that showed the vortex structures clearly. Clearly, the vortex, well, this is, we still use isosurface. You see, starting where it's a flat plate, we add some perturbation, where we use DNS, and we can see how this vortex formed, you see, from the beginning. Then become, larger vortex. There's a transition zone. And then become chaotic. That's turbulence and a fully developed turbulence. So we do this, as I said, long time ago. Well, if we see on the top, to see the vortex structure. That's made by Nutex as well. Well, you will clearly, but sorry, I still didn't give much, theoretical work on the turbulence, not yet. But we have the same problem is everywhere. We need more students to join this. You see? From my point, what this? Well, we think this is LNES supports. And we think LNES is a solution. It's more close to exact solution. Then we see what? We see how laminar flow to become turbulent flow. What do we see? You can find that. How the flow, well, originally we had nothing. The flat plate flow, nothing. But when we add some perturbation in the inflow, then we find it clearly tell us how from laminar flow this is nothing, laminar flow. And I think this is a transition zone. Transition zone means more vortex formed. Originally, we don't have any vortex. Then more vortex, larger vortex, and small vortices are formed. This is your transition zone. Then here we see the flow lost similarity, not symmetric anymore for this. What that mean? That means laminar flow become turbulent flow. Then the question is, what's the mechanism? What's the theory for laminar flow to become turbulent flow? You ask me, you ask DNS, they tell you. The problem is we don't have enough manpower. We didn't study it. They all tell you how laminar flow become turbulent flow. Well, you have many turbulent theory. Well, it's very hard to convince me. But I say, ask DNS. They will tell you why laminar flow become turbulent flow. Okay? We need to carefully study this process. This will tell you the theory how laminar flow become turbulent flow. We maybe have 10 theories, I don't know. We have many theories, bifurcation, transient growth, we have many. If there is the theory for flow from laminar turbulent, they have vortex structure, they have impact vortex, so many in the literature. Yeah, you can find it. You can find many. Vortex breakdown. Well, let's say, you ask me if they're correct or not correct, I only can say, I don't know. I'm not sure. But look at this. They clearly tell you how laminar flow become turbulent flow. You ask the physicists, you ask DNS for physics. How this big vortex formed, how they create small vortices, how they become chaotic. They have physics. Well, Well, then you ask me, well, the book says vortex breakdown. Well, we didn't see it. Where's the breakdown? We didn't see it. You say, there's a bifurcation. Where's bifurcation? We didn't see this. You can give hundreds of theories, but it's hard for me to understand, to believe. As I say, I don't know. Our only answer is I don't know. But we need respect the, fact, respect the science. What science tells us, that's the truth. I'm not sure you guys, a lot of young guys, you are starting, maybe started the turbulence. Turbulence is still, a mystery for science. Even people's civilization for thousands of years, where turbulent research for a couple hundred years. This is still challenging. What caused the turbulence? Why turbulence can be sustained, created and sustained? I believe they must have some physics. Well, anyway, they must relate it to vortex. You don't agree, I don't agree. But there it is. If no vortex, you say we get turbulent flow, that makes no sense. If it's related to vortex, unfortunately, what's the people's answer? People answer say, vortex have no definition. The scientific answer? The scientific answer? Vortex has no definition. But the turbulence equals to vortex. What is this? You see? What is this? Turbulence. What is? They're very close to, link to each other. You say, we don't have definition for vortex. That's the correct answer? Yeah. That's the problem with our education. we tell the people, the student, wrong thing. Wrong concept. Okay? So that's why we should have this, short course here. So, if we don't agree with my point, raise your hand. We can discuss it any time. That's why I say, if you find one counter example to my theory, well, I should have knew this classroom. Or I should claim my whole theory is done, is finished. Okay? Let me continue. You have questions? Does I say you have questions? You may, well, my words is, yeah, you have questions? No? Everybody. Well, as I said, this is a discussion. This is, I'm teaching your student, not that case. We are colleagues. We are work together. Yeah. But some people asking me, why you have not retired? I'm not young. Yeah, yes.
A couple of comments.
Yes.
Once you create turbulence, the entropy has to increase, so you're going to sustain it.
Yeah.
Okay?
Yeah.
The second comment that I would like to make is that sometimes in numerical simulations,
Yes.
you always get numerical turbulence. Okay?
Yeah.
In physics, I understand your point. How do you go from a laminar flow, to turbulence?
Yeah.
That really creates it.
Yeah.
Once you create turbulence, then you're going to sustain it.
Yeah.
But we have to be careful when we are doing simulations that actually there is also some numerical turbulence coming in, because we are not ideal the equations.
Yeah, that's true. Yeah. But we know that depends. Yeah, and we cannot say. Yeah, you are right. We cannot say our influence is clean. Even you clean, it's not clean. Yeah, they maybe have some numerical simulation growing. Yeah, that's the second question. The first question, we also need to be careful with that. That's a different. We need to study the mechanism for sustenance. But we did. We did, yeah. This is not just a symbol. Why they can sustain it? Because we have energy transform path. If we don't have energy transform, you cannot stay in it because you have dissipation. So the turbulence will become weak and disappear. So they can sustain. Well, that's cost us two questions. One is sustain. The other one is numerical also could have some kind of perturbation. Well, for example, bypass transition. Well, this could be a question. Bypass transition, you didn't see this. You didn't see this clear laminar transition turbulence. They directly turbulent flow. But that could happen. Then how you say? Well, but I believe the conclusion still stands. What's the conclusion? First, turbulence must have some kind of mechanism for sustenance. They must have some energy transfer. Yeah, that's one. The second, because your turbulence generated somewhere, you don't need transition directly coming in. Then bring the turbulence in. Well, that's no contradiction. We talk here is about natural, how laminar flow to become turbulent flow. That's what natural. But do we have natural? We still have natural. Especially like NASA, I think they talk, missiles or talk about space science. Well, they do find this kind of physics from laminar flow, transition, and turbulent flow. Or even ships, they very transition zone very small. There's still such a process. So, well, of course, they could have others because the real world is complicated. Yeah, not just like this. This is just one example. Tell you how the laminar flow become turbulent flow. As I said, we have not enough manpower. We did this maybe 10 years ago or more. But we didn't do very detailed analysis. No, we do some theoretical analysis, not very details. Yeah. Okay. Well, then we talk of three generations. Why is there three generations? First generation is vorticity. So I don't want to, what's time? And you 10 o'clock, right? Yeah. Okay. First generation. First generation, I think, is given by Helmholtz, the German scientist, in 1858. Yeah, he published a paper, but it's in German, not in English. And in America, we only can see the English translation. We don't understand the German. We don't know what he really said. But from his English translation, what they say, vortex is they call the vorticity phenomenon. Yeah. But this really is vorticity lines. So based on this, I think, and based on his three Helmholtz, theorems or Helmholtz laws, we built up the vortex dynamics. So the modern vortex dynamics is based on the Helmholtz three laws and all three theorems. Unfortunately, these three laws or three theorems are misunderstandings. None of them is correct. None of them. Unfortunately, yeah. But this is our base for the textbook, for the all online lectures. Well, second, we just, today, I will first talk for second generation, I think it's in 80s and 90s, you know. They give a lot of identification methods, and a kill method, a lambda 2 method, a lambda CI method, delta method, a lot or many similar methods. This is based on the eigenvalue of the gradient, velocity gradient tensor. That's the second generation. Well, first we talked about first generation. Well, vorticity is clearly mathematical definition at a point. Well, don't attack, don't criticize. They criticize. Then new tech is 1 point. It is not. It is not the global moving. It's not a global motion of fluids. Well, what is it saying? Don't attack that. You attack what is it? They're both same. 1 point. Okay? This is clearly mathematical definition. This is Q of the vorticity. Okay? That's clearly. Well, that's Helmholtz 3 theorems or 3 laws. One said the strength of vortex filament is constant along the length. This theory really tell us, if vortex formed, they call vortex vorticity tube, they can never disappear. Otherwise, violation this law. This law is the strength is the same. They never change. This strength they talk about, I think, this called flux or something like that.
Here, the online attenders cannot hear you.
Cannot hear me?
No. I mean, if you stand here, they can hear you.
Okay.
Good, but if you stand
This
here,
is this. Okay.
there are echo.
Okay. So, what did it say? Yeah, according to say, if the vorticity or vortex, they call it vortex, if created, they never disappeared, never. Well, then we have more vortex. Well, how many people already live in this earth? How many vortex we have, we don't know. But according to his theory, never can disappear. Yeah. The reason it is you don't have pens here. We can write something on here, right? Well, this is just saying that this is that's the we talk vorticity, or they call it vortex. Yeah. But we know this. So when, according to their theory, when vortex created, they never disappeared. You cannot disappear. That's Helmholtz's first law. Second law, it just says only the water filament, are called vortex, only can end in fluid. That means you can only end inside the fluids. That means a circle. Or end like this, either on the surface or on the infinity. What is it say? The second, The third one, well, this is really wrong. This is really wrong. Why? Well, you can, when I said what is the omega z? It's a partial, v partial x, right? Because on the surface, v is 0, u is 0. V is 0, u is 0. Well, of course, the omega z is 0. This second law violates the first law. How the vorticity, flux to be 0? How to do that? You say, that's your vortex. Every cut normal is the same, according to first law. So the second law against the first law. But unfortunately, if we check website page, still a lot of things like this. They say vortex only can end on the surface. No, never. Never. Well, the mathematical, I think, proof is very easy. Everybody, I think, is qualified to prove that. Everybody here can prove that. The omega z is 0. The omega z is 0, what happened? You have vortex. The flux, same. If it's 1, everywhere is 1. Flux. But the surface is 0. 1 becomes 0. That's directly against the Helmholtz second law, directly against the first law. Well, do you have a different opinion? As I said, because the web page you can find many places, it say vortex only under the wall or under the infinity. Well, infinity, we don't know where it is. Where it is, because as I said, if I move, I generate vortex. This vortex could be moved from here to Europe, to China, then come back to here. They must come back to here. I generate vortex because what? Vortex cannot be stopped. You understand what I'm saying? There's no way. They cannot end in the wall. No. Wall is 0. But they make nonsense. So everybody, you are qualified to prove this. The Helmholtz second law is wrong. Third theory. Oh, sorry. In the absence of rotation, external forces, a fluid is initially irrotation. That means if the fluid is outside the vortex, you can never enter the, inside the vortex. Inside, always inside. Outside, always outside. Well, this is against the basic knowledge. Well, if we don't believe, I'm not sure there's nobody from the atmosphere science maybe could surface some. Yeah. Well, that's not realistic because we cannot find the Florida hurricane. All of the stuff is from South America. It's not the truth. Because vortex inside material, always inside. Outside, always outside. I don't think. I think the hurricane damage Florida material, house, the inside vortex. Not from South America. From Caribbean, not that case. So unfortunately, this is our textbook. This is our web knowledge, web, But unfortunately, they are all wrong, all misunderstandings, all misunderstandings. Also, we still teach students every day. Well, if we don't agree, stand up. Talk to you. You are wrong. You're wrong. You made a mistake. Make a misunderstanding. You can welcome to do that. Well, I'm not sure you understand what I'm saying. What I'm saying. Well, all these three, theorem or three laws, no scientific foundation. No scientific foundation. Yeah. You very easily you prove that it's wrong. Well, that's in the book. You say wrong. That's in the book. Well, does the book still use new edition? Still used in every university, many universities. Where they say, what's the vortex? Vortex is what is the tube? On the surface, the vortex line is vorticity line. They clearly shows that. In a new, I think this is pretty new, 2015, not too old. Yeah, it's clearly showing that. Yeah, you see that? This is vortex line. This is vortex. This is vortex line. Well, this is they say the streamline. They say this vortex line is the vorticity vector. It is a vorticity vector. On the other hand, just say this vortex line is parallel to vorticity vector. I don't know. We cannot, criticize the author. Author may never did the DNS. They never get the DNS from vortex because they just copy from somewhere. But you guys could do DNS. You checked. You checked the vortex. You checked the vector to see if it's parallel to vorticity line. Is parallel or not parallel? Unfortunately, well, our student did well. They're not parallel. They're even orthogonal, not parallel, orthogonal even. Vorticity line is orthogonal to vortex line. How to say vortex is a vorticity tube? It makes no sense to me. Well, there's another book. You could say, well, they're both the same. The vortex line and the vorticity line. So you see that? The omega is a vorticity line, vorticity vector. This is a vortex line. They say the vorticity line is parallel to vortex line on the surface. So vorticity line form the vortex. That's what they say. The textbook say. That's textbook say. Yeah. Unfortunately, every university use. I think all of American universities use these textbooks. Not one the other. Maybe different textbooks, but they're same. Their opinion is the same. So what I can say is vorticity tube. What on the surface? What surface? Surface is parallel to the vorticity vector. That's what I say. Okay. Then we see. Well, that's I think Jie Wu. I think he's also of vortex dynamics, but he said. It's 2018, he said, definition 1, a vortex is a vorticity tube surrounded by rotational fluids. That's his definition. What is published in the Science of China, I think. Clearly, it says vortex is a vorticity tube. I think even in the encyclopedia of mathematics, they say a vortex is defined by the vorticity in the fluids, which measures the rate of local fluid rotation. Yeah, they say vortex is measured by vorticity. The strength is measured by vorticity. So vorticity is large, the rotation is large. Well, that's in the encyclopedia. Well, it is very clear, very clear. Yeah. I'm not sure. There must be some people are suspicious, but they just don't speak very loudly. So I just speak loudly. I say, well, this makes nonsense. It's a misunderstanding. But some people suspicious, but they didn't speak loudly. So you understand what I'm saying? Anyway, before 2018, most of the people think vortex is vorticity tube. Vortex strength is measured by vorticity until now. Now, the majority paper, research report are still use this concept, I think. Okay? That's I talk about the past. So far, any questions? Any questions? Let us have with no rush. No rush, it is important. Well, we need to see if with well, as I said, this immediately you get a contradiction. That's what I claim at the beginning. One counterexample is good enough. We don't need two. We don't need two. That means one. What is one? Yeah. Well, vortex is a natural field. Vorticity is a mathematical definition. How do we know they're same? One is what? It say if we have channel flow or we have laminar boundary nail. We have laminar boundary nail. What happened? What happened? We laminar flow. What do you mean laminar? The flow is layered. They don't have any vortex. Don't have mixing. Right? But vorticity is larger. If the velocity is large, near the wall. Vorticity is large. Vortex is zero. How we can say vorticity is vortex? How we can say that? How we can say just like in the book or in the research paper, in the journal, how to say vortex is measured by vorticity, how to get a conclusion that one is enough. The laminar flow or laminar channel, we don't have any vortex, but the laminar have a vortex. But we have big, large vorticity near the wall. How vorticity equal to vortex. How can do that? One is 0, one is 100. How we get 0 equal to 100? How get that? How to get this conclusion? Okay? And that's I said. Well, that's I said. One is good enough. So we said vortex cannot be described by the vorticity, cannot be measured by the vortex, cannot vorticity, cannot be detected by vorticity, cannot be as I said, cannot be measured by vorticity. Anyway, cannot. Cannot. I don't care about it. He said the book said, the website said, the MIT, online lecture said. Why you say no? Well, give counterexamples. One counterexample is good enough. Yeah, I think. Okay, but but I hope you can give me counterexamples. So why say, well, no, we cannot trust this. We cannot. Okay. Well, more serious. Some people give me a warning. Dr. Liu, we need to follow the Stokes theory. We need to follow the Kelvin theory. This is mathematics. They cannot be wrong. So Dr. Liu, be careful that you against mathematics. Well, and this is really serious. I cannot against mathematics. Mathematics is logical. Well, this is an example for the first one. As I said, we looked at the omega Z is very large, but we know laminar flow we don't have. Let me look at the other, This is a more serious misunderstanding. They say we have Kelvin theory, we have Stokes theory. This is all mathematics. How you can against mathematics? Well, this is laminar flow. Remember, this example is laminar flow. Okay? We know that vortex zero. We know that. But if we count the circulation, it's not zero. It could be very large. When you use the Stokes integration, when you use that, you said this is something like that. That's a Stokes theory. That cannot be wrong. That cannot be correct. But your conclusion is wrong. What the conclusion said, circulation is large, vortex is strong. Well, we give one counterexample. Look at the laminar flow. Circulation is large, vortex is zero. We don't have rotation. Where is the vortex? Circulation is large. Well, the people say that's common sense. Circulation is large, the vortex is strong. That's common sense. Why are you against that? Well, I just tell them, misunderstanding. Circulation is large, vortex is zero. Well, what's wrong? What's wrong? Well, the wrong is very simple. I know this is large. This is large only mean vorticity is large. It doesn't mean rotation is large. Because vortex, is not vorticity. Well, this is more common misunderstandings. I can see many places. Also, they give me warning. So this Stokes theory, how Stokes theory can be wrong? Stokes theory cannot be wrong. But the vorticity is not rotation. Do you have any different opinion? Well, as I said, we just live in a misunderstanding world. Misunderstanding what we live. But, you guys is very intelligent, very talented. You understand what I'm saying? How about the regular people? Regular people, they never have, education about fluid dynamics. What do they think? Of course, they listen to you. They listen to the book. They listen to the website. Unfortunately, all of these concepts are wrong or misunderstanding. Any different opinions? As I said, you give me, you raise a hand, right? You give me, you say something wrong. I just say this is wrong. People think circulation is large, vortex is wrong. That's wrong. That's wrong. We don't have such. Yeah. Okay. Well, actually, some people have similar idea, like Robinson. In 1989, he said association between the regions of strong vorticity and actual vorticity can be rather weak in the turbulent boundary layer, especially near the wall region. Well, 1989, how many years? You see? Yeah. 1989, almost 40 years. Yeah. Robinson said that. He found it. He by his experiment. Well, people know his opinion, but people just didn't, stand, speak out. Okay, he found it. We have found it as well. Well, this is found by one of my students here. He just, draw the vector. This is supposed the gray one is supposed to vortex surface. What is vorticity? How are they parallel? How are they parallel? They maybe have 45 degrees. They maybe have 90 degrees. And very few 0 degrees. Then here, he also, that's from DNS results. Yeah, that's the vortex. Well, I think we cannot find it, you see. He find that there's two. One is the, mutex, I think. The other one, it is vorticity. But I'm pretty sure the mutex is vector. The mutex vector is parallel to surface, not vorticity. All vorticity are cross, even orthogonal to the vortex. Yeah, he did quite a number. He said, that's the vorticity, that's the mutex. Mutex is parallel to the surface, not the vorticity. They are different. If we don't believe, you test it. I think that now every university has such capability. Use some DNS results. You can draw the vortex, then you can draw. You say, I don't trust the mutex very much. You use Q. Use Q, you get isosurface. Then you draw your picture, mutex and the vorticity. You'll find which one's parallel. Yeah. Well, we find this as well. Well, this color means the vorticity. This green one is a vortex, laminar vortex. Well, it is just the opposite. We think vortex, inside vortex, vorticity must be very strong. Outside, vorticity must be weak. That's just the opposite. Inside the vortex, the vorticity is weak. Outside the vortex, vorticity is strong. It's just opposite. The conclusion just the opposite. That's clear. This is from DNS. Well, you can do as well. Well, if you say we didn't do DNS, well, you can use the website to find the DNS data. We have the data as well. You can check that. Well, just the wrong direction. And you will see, this is the vortex, pretty much the vortex. But this line is a vorticity line. You say vorticity line is not parallel to vortex line. Vorticity line even orthogonal or cross vortex. Well, this is, we are pretty sure. I think Costa is also know that, the vortex is not a vorticity. If you draw the vortex line and vorticity line, they're different. They know that. When we have share, well, boundary layer we have share. If not share, they're same. But we'll talk. We will talk that, because that's your vorticity. If we share 0, of course, vorticity equals to mutex. It's the vortex. The relation is very simple. Relation very simple. But unfortunately, we can never get rid of share. We cannot. No matter on the earth, boundary layers, even in the space, we cannot get rid of share. Unfortunately. Well, this is also true again. Again, it just say, well, you look at that, what is it is small in the vortex. Yeah, you can see this. Second, we talk about second. I don't have much time. We don't have much time. I just quickly finish. Well, the second, we know that we have many. Yeah, we have all based on the gradient of the velocity. Then the velocity gradient is represented. Well, there's a lot of problems. I think there's even more problems in our textbook and in the wiki, even in the wiki. There's a lot of problems because how to write this velocity gradient? How to write this? Yeah, this is I believe this is from the wiki or from our textbook. This really is wrong. The reason why it's wrong, because the correct one should be this. This is the correct one. Well, they're same. Nobody cares. They either write this way or write this way, like the textbook or like the wiki. They're not same. Mathematically, totally different. How to say a matrix A same? Mathematically, you cannot say. What difference? They have same eigenvalue, but different eigenvector. Be careful with that. You look at the book carefully. Yeah. So, yes.
But I think the problem lies in the fact that actually eigenvectors are only used enough to define the axis of the vortex. So basically, you're not interested about the direction.
Yeah, right. Yeah. Well, you really transpose. You get another eigenvector. The other eigenvector is not a Newton. It's not a rotation axis. One is, but well, the eigenvector have definition. When we transpose the matrix, we change the eigenvector. Be careful with that. That's all not. Well, we say we check. Well, this said. I think. Well, I don't think I have time to talk about that. It's too long time. So I just maybe, I just say, well, this is important. That's my opinion, but that's not in the book. Well, people talk about dot product, cross product, and but for the matrix don't have dot product, cross product. Matrix doesn't have. People mix the physics and mathematics. So, from my opinion, the dot is a dot product. You cannot throw away the dot. People randomly put the dot through the dot. They think the same. There's a multiplication. But that's wrong. That's wrong. When you move the data, you need a transfer, you see? It is the gradient wave. You need when you remove this data, you need to become, then you get the same answer. Be careful with that. That's the people, mixed. The vector is a vector. It is only unique. There is a vector always there. But the matrix, all we say is a vector matrix. Could be 100,000. It depends on coordinates. When you talk about the dot product, that's a two vector or two matrices or matrices with, there is, have physical meaning. But mathematics don't have. They only have is a metric multiplication or inverse. Well, the like division. People mix them. They randomly put this dot in or out. Don't forget it. And you put in, this become the left hand side should be inverse. Add again. You cannot randomly do that. That's a mistake. That's the original definition, as I said. And then we move the data, the physics. Is the tensor dot vector. Tensor dot vector is projection. Mass don't have projection. They just two matrices. The product has become this. This is dV. That's the velocity gradient. Well, from this, so we talk about a little about we call the Helmholtz velocity gradient. I remember I studied the fluid dynamics. The first, class is about the Helmholtz, velocity decomposition, or more mathematical. They call the Cauchy-Stokes. That's decomposition. That's the gradient of velocity become two parts. A and B. A is symmetric. They usually call it strain, tensor. B, they usually call it rotation. That's a mistake. B is not rotation. This is vorticity part. This is vorticity part. They say this is strain part, this is rotation part. This is misunderstanding. We only have a symmetric part and asymmetric part. Symmetric part may be related to strain. Anti-symmetric part related to vorticity, not rotation. There's no concept for rotation. Okay? That's the traditional. This is traditional. That's in the book as well. I will talk in the last section, the afternoon. We talk about it. Well, this is could be good. Symmetric and asymmetric could be good for laminar flow, not for turbulent flow. A turbulent flow, we cannot do that. We cannot do this. Well, then they say there's a PQR. And this eigenvalue equation, they call characteristic equation of the matrix. Yeah. Then you can find this lambda 1, lambda 2, lambda 3. The 3 lambda. But for rotation, we say, we know that. For rotation flow, they 1 real and 2 complex. Complex must be conjugate. We have no other choice. Either way, 3 eigenvalue or 1 real eigenvalue, 2 conjugate. We have no other choice. Only 2 choices. Well, physics, we call this vortex and non-vortex. Or we call it rotational or non-rotational. This, described by the mathematics. This is mathematics. So this is characteristic. You get a P, well, you get a Q, you get an R. P in general, it is a trace, Like incompressible flow is 0. Incompressible flow is 0. Q, they call it rotation. That's for the second generation. They use Q to charge it. Charge it rotated or not rotated. Or maybe play some role. So the Q criteria is most popular now. And so I think it could be most popular. Vortex identification. Well, they very clearly they defined by the B. That's the F, Frobenius norm minus A norm. Well, they define it. If Q greater than 0, define then it's vortex. If less than 0, it's no vortex. Well, the Q is now is most popular vortex identification method. But this has nothing to do with vortex definition because it is scalar. Well, vortex cannot be scalar. Not only this. Or the delta. So it is given by Perry and Chong and Perry, 1990. They just use delta determinant, I think. They just use determinant to, because the determinant is greater than 0, and then you have, two, I believe, complex roots. If less than 0, you have 3 roots, real roots. This is delta. The second, and I think, really, Q, is most popular. It is not only this, not only they are, scalar, but they have theoretically problem. There was theoretical problem. If you study Q and delta, delta is a rules. Delta greater than 0, you have 1, real root and 2 conjugate root, eigenvalue. But when Q less than 0, it doesn't mean delta less than 0. Because it has R squared. So Q is next to 0, they judge this is no vortex. But the delta say it is a vortex. So Q have theoretical problem. They mistreated rotate zone to be no rotate zone. Not only accurate, not accurate, physical meaning, or is scalar. Not only this problem. Theoretically, well, for some engineering research, it may be okay. For scientific research, we cannot use this because they give wrong definition. We cannot do this, as I said. But this is really serious. When Q less than 0, they say it's no vortex. But delta greater than 0. Delta is a principle we must follow. This could have been, mistreated. Could have been. Well, lambda CI, we know that. That's just the, imaginary part of the eigenvalue. Well, I think this lambda CI is most close to Nutex. But it's not exact same. I think they do some, comparison. I think Oscar did. I'm not Oscar coming, or you don't know either. Okay, he said he will come. He did some comparison. That it's not same. Lambda CI is not same as Nutex. In the period, they big difference. But they call it swirling strength. Well, the real problem it is they use this vector, I think, but use this really is like the matrix 3 vectors is matrix. Yeah. Then you reuse, but the problem is that it's not an orthogonal system. It's a non-orthogonal system. Non-orthogonal system, you cannot get exact rotation. So that's the nominal CI with a nominal CI problem. They didn't use orthogonal system, but Nutex used orthogonal system. Yeah, that's different. Yeah. Well, lambda 2, yeah, I think there's some experts here. And lambda 2. Well, lambda 2, it is try, to get the, smallest the pressure. They say it is, the vortex center. The vortex center, the pressure is smallest. It looks like could be true for some area, not all of the area, not all of the area, and not in the deeper boundary layer. But even so, because they ignore the viscous term and ignore the time-dependent term, it in general cannot get the lowest pressure. So they cannot be, consistent. And that's a nominal 2 problem. Yeah. Also, they assume it's incompressible. Be careful with that. Q, incompressible. Lambda 2, incompressible. Nutex, nothing related to compressible or incompressible, or nothing related to any dynamics. Nutex is a mathematical definition, only responsible for this velocity field. They're not related, no assumption incompressible, no matter hypersonic, supersonic, incompressible, no speed, no matter. General, no matter thermodynamics, multiple phase, combustion. It doesn't bother anything with Nutex. You understand? Some of them, like lambda 2, I believe is related to the fluid dynamics because they get from the incompressible Navier-Stokes equations. So if you change the compressible, as change, and thermodynamics, they change it. Multiple phase, they change it. Nutex, no change. Well, they just say lambda, because they say, well, if, I believe they check this system, if the, I think the John who said, define this system, A squared plus B squared, this system, they try to find a minimum value. Yeah, then it's called a definite negative. Definite negative, if 3 eigenvalues, 2 eigenvalues smaller than 0, they think this place is a vortex. So that's the basic idea. Yeah. But as I say, the idea is good. Yeah, but the problem is you ignore the time-dependent term, you ignore the viscosity, you assume incompressible. So there's too many assumptions. Well, also, we passed the time. I think I should stop. I can continue to talk. Well, the last slide show all of the Q, delta, lambda 2, or lambda CI, well, they're not a pure rotation. Only Nutex is a pure rotation. You see, you can find that. Q, you have, I believe you have shear, you have stretching, delta more, and lambda 2 you have something. So there's no pure rotation, no pure rotation. That's what I say. Well, that's, I just simply listed these people. I think I should stop here, but as I said, this is the informal discussion. So we talk somewhere, we can stop somewhere if we have questions. Okay? So let's take a rest. Yeah.
I have a question.
Uh-huh.